Great. I hope you had all a great lunchtime. I would say we're going to continue. And before I forget, the signature list that you need to sign. All right. Maybe let's shortly have a look again at the task at hand, which is like following. So you already heard about the carry look ahead adder during the lecture. And we're now going to have a look at figure 9, which depicts a carry look ahead adder, but it is constructed using 4 4-bit carry look ahead adders to realize a 16-bit addition. And the question here is now, how do we come to C out? How do we create that? And for that, we wanted to find the carry look ahead logic here. And we have the inputs G and P, which is generate and propagate. And we also know that this is a CLA, so a carry look ahead adder, which probably has similar things inside. So it also has like generates and propagates depending on the bits that go inside. But maybe first of all, also like a short recap, what are carry look ahead adders and how are they defined, how does this work? So the basic idea is here that we want to find a different representation of the next carry. Because if we don't, we just get a very long carry chain, and other description of that maybe allows us to find different ways that do not need these long carry chains. And this is also what a carry look ahead adder really benefits from. So what is the basic idea behind that? So instead of thinking, do I need a carry or do I not need a carry, we think more like, do I propagate or do I generate a carry? What does this mean? So maybe first thing is like, what happens if A and B are both 0? So this is like this case here, right? If A and B are both 0, then we definitely don't have a C out, right? And what happens if C in is 1? We actually also get a C out of 0, so which is then killing the carry, which is why it is referred to here as killing. Then we have the second case where A and B are unequal. So that's the case here, that's the case here. And what we see is, we don't have a carry, so we also don't have a carry at the output. But what happens if we have a carry in? Then we see, okay, we have a carry at the output. So what happens? The carry of the input just propagates to the output. So as soon as A and B are unequal, we have a propagate of the carry. And that's now the third case. How do we generate one? So this happens if A and B are equal, independently of whether we have a C in or if we don't have one or we have one. In both cases, we definitely will generate a carry. So this is like the idea, just a different description of it. And now the big question is okay, how do we use the generate and the propagate now to form this carry? And it's nothing else than just like either we have to generate, then we definitely gonna generate a carry, or we're gonna have a propagate, and then it's dependent on the carry in, right? So either we have propagate and carry in then. So this is like the basic idea behind it. And so how does this work like for a carry look ahead adder now? So the first carry, I guess, is very easy to understand. We have our generate, we have our propagate, and we have our C0, and that's it, right? And how does this look now if we have a second bit? So then actually we have a very similar formula. It's like G1 or P1 and C1. So this looks very similar. But now we can exchange the C1 here by this formula and then end up with something like this, right? So then we have our G1, either G1 generates, or we have a P1 and a generate at the stage before, or we have a P1 and also a propagate at the stage before and a carry in into the stage before, and so on. And this is just continued until you have all bits. Okay, this for a short recap about this different representation of the carries. Are there any questions regarding that, or is that clear so far? No questions. All right. Then let's continue with our task. All right. So this is more or less exact the same thing, right? So this is our propagate is defined. This is our generate is defined. This is just like looking here. If we have unequal A and B, then we have propagate. If we have the same, then we have a generate. And now the thing is, okay, we have such a processing element here, right? And this is our P out and our G out. And now the question is, how do we come to this P out? We just take the two P's from the input, so Pi and Pj. And for the G out, it's a little bit different. We now take the generate of the first, so of the left one, and or we have a propagate here at the first one and a generate at the second one. So this is just how it also was defined during the lecture, right? And now the question is, maybe one step back to the figure of the question. So first question is like, what values do P0, G0, P1, G1, and so on have? And this is what we're gonna answer now. And for P0, so P0 is dependent on the first input bits, right? So this is the first 4-bit CLA. So in order to come to that, it's just the ending of the propagation of all the bits inside, right? Of the propagates inside. And you do the same thing for P1. These are dependent now on the bits 4 to 7. And so on. We do the same thing for P2. These are then dependent on the bits from P8 until P11 and so on. And for the generates, you also do exactly the same thing, right? So for G0, you get, okay, it is dependent on the 4th bit, so on bit 3, and the generate on this one. And if G3 does have a propagate, then this also is dependent on G2, so you do P3, G2, and again the same thing. So P3, P2 propagate, then if G1 has a generate, then you set G0 and the same thing, and so on. Questions regarding that? No, okay. And now the big question is how do we come to the carry logic, right? So the carry logic is then defined as G0 or P0 and C0. And this is like actually the same thing as G0, because what we know out of the figure or diagram is that C0 is 0, so we don't have this part here. And now what happens to C2? So C2 is then like G1 or P1 and C1. And if I just plug in this formula into C1. Then I come to this result here. There's again the C0. Because C0 is 0, this part can just be neglected. And that's it. We do the same thing for C3 and C4. Okay, other questions so far? No. Okay. This already tells the answer. Then we use this one. So the question now is, what is the advantage and disadvantage of a carry look ahead adder? And the idea is like that we draw some circuit that supports our reasoning. So maybe first thing, what do you think like is an advantage of using a carry look ahead adder? Any ideas? All right. So to answer this, a short diagram of a carry look ahead adder that accumulates 2 bits. It looks like this. You have your half adders here, and you have your carry in here. You have your 2 output values here, and this is the carry out. So what's the benefit compared to a ripple carry adder, for example? So obviously the ripple carry adder has a very long path, right? Because the signal here needs to traverse through all of the other signals, and this is not the case here anymore. And this is why a CLA only has a few gates in the critical path. Then it's like it has like this layering approach, right? So you just have one layer of AND gates, this one, then one layer of OR gates, and some pre-processing and some post-processing, and that's it. And this kind of is also like the depth of the critical path, how deep as it gets. All right, then let's talk about some disadvantages. So the disadvantage here is like that the gates are much slower and also need a higher fan in and fan out. So why is that? Maybe one slide back. As you see here, you have here this AND gate, right? And this AND gate depends on the propagate of this one, on the carry in, and on the propagate of this one. So let's assume we have multiple more bits to add. Then you would end up with a large AND gate here that is dependent on all of those other half adders, right? So this gets to a very large fan in. And why is a very large fan in a problem? So this is going to be explained by the following. Have you heard of CMOS dimensions before? So how do you dimension the transistor sizes inside the CMOS logic? Not really. Okay. Then I'm going to do that. Maybe we leave this here so far. All right. So let's draw a simple inverter, right? This looks like this. I guess you've seen that before, right? Yes, perfect. So this one is our PMOS transistor, and this is our NMOS transistor. Have you had a lecture regarding how such a transistor is built up? Yes? So you know that this is silicium, that then a N or P well is added to those, right? So, okay. And the thing now is that NMOS is comparable to PMOS, much more less resistant. So meaning that the charge carrier in a PMOS, they are not as how do you call that? Are not as willing to move, right? As in an NMOS. So this means that a PMOS transistor has more resistance than an NMOS transistor. So Why is that an issue? Great question, yeah? So what happens now if in toggles? So it goes from 0 to 1, for example. If it goes from 0 to 1, then this one was open and closes, and this one starts to open. But this means now that this one is closing not as fast as this one is opening. So this means that switching from 0 to 1, this one is a lot faster, right? Then, okay, maybe I describe a little bit differently. So let's say NMOS is faster, probably like 2 times. NMOS is slower, also like 2 times slower than an NMOS. So meaning that if we switch and the output gets 0, we get a lot faster the 0 here than we get a 1 here. And that's something you actually don't want, right? Because what you actually want is that this thing is symmetric. If you don't have that, the timing of your circuit is very hard in the end. And what a CMOS designer then does is like, it dimensions the PMOS 2 times larger so that the resistance of the PMOS gets 2 times lower and is exactly as fast as an NMOS. So then you balanced your design. So this means what you usually do is like, let's say, let's use a different color. So if you talk about dimensions, a normal inverter would then be the NMOS dimension would then be 1, and the PMOS dimension would then be 2. I hope this makes sense so far. And now the interesting part begins. So what you usually then do, if you create a NAND gate, a NAND gate looks like this, right? So the NMOS are then serial and the PMOS is parallel. So this is how you usually design CMOS gates. So the design of CMOS gates is something you've heard before? Yes? All right. And now the question is, how do you dimension this? And you do that like, okay, here we already know this one is 2 and this one is 2 as well. So they both are exactly, both are exactly as fast as the other one. And now the question is, how would you dimension those two? If you would do something like this, because that's what we did before, then what happens? These are more or less 2 resistors in series. What would you do then? It's just like the addition of the resistance of both of them, right? So then they would end up like being 2, and 2 is like, no, actually we have a problem, right? So what would you do now? So either you could then make those 2 faster, right? So you just make them wider. Nevertheless, as you see, the more inputs now would add here, the slower this path would get. So you would need to make your resistors very large. And this is why a high fan-in makes an issue. So you cannot support a very large fan-in because you would need to size your transistors very, very large. And that's just not possible, and at a certain point doesn't make any sense. Questions? All right, so next question is about the serial adder now. You've also heard of the serial adder during the lecture. And now we want to know its performance metrics. So we want to know the critical path and the total latency. If we want to add a 16-bit number, we use for this a single full adder and some shift registers. remember that the critical path of the design can be calculated by calculating the number of NAND gates in the longest path between the two registers. All right, so first thing we need to come up with is like, how does the serial adder look like? How does this work? And this is like the figure you should have all seen during the lecture. And what it does is like you have your shift register for one operand and a shift register for the other operand. And what you do is like you just take the LSB out of both registers, add them, take the resulting bit and store it in another shift register. So that's the first thing you do. Then you have added your first bit of your 16-bit value. And then it's important to also store the carry for the next operation as carry in. As soon as you have done this, you shift those two for one position. Now the bit next to the LSB is at the LSB position. You take that, do the addition, shift in here the result, update the carry, which then is used for the next one as a carry in, and so on. And you do that until you've calculated all the 16 bits. So short recap, how do you do the addition? It's just XORing. How do you get your carry? It's the usual formula here. So A times B or A XOR B and C. So now you get some numbers for the delay elements. So this is AB. This has an area of 1.5 gate equivalents and a delay of 1.5. Then you have your A or B, which is a bit larger, but the same delay. And this is your XOR gate, a lot larger and a much higher delay, which you have here. And now the question is, what is the delay and what is the latency? I give you like 5 to 10 minutes. So maybe as a small hint here. So we want to have the path delay actually of the adder itself. So first we start with the adder structure, which is like the full adder, right? And these are the formulas for the full adder. So have a look at those functions, see what gates you need to realize this function. Think about what can happen in parallel, and then you come to your longest path. All right, then let's see how many gates do we need for SI first. So let's focus on the adder first, as I said. And what do we need for SI? So these are 2 XOR gates. So that's like calculating the first XOR, putting the result into the second one and using CI. So we need 2 XOR gates. This is then like 2 times 3 GE, giving us 6 GE. Then we have Cout, which looks a little bit more complicated. So starting at the most nested operation, this is A XOR B. Then we have a AND of the result, which gives us this one. And then the next operation is like the ORing with the result of A and B. And why is A and B not reflected in here? The reason behind this is that A and B, the calculation, can happen during the time the calculation of this one is happening. So we get 3 GE plus 1.5 GE plus 1.5 GE resulting in 6. Is this clear so far? Questions regarding that? Yes? The GE? Yeah, it's just on the right side. Where? Where? 4? CI? So that is what I just tried to explain. The thing is like we're looking at the path delay, right? So thing can also happen in parallel. This one, the calculation of AI and BI can happen in parallel to the calculation of this one. So this is why it is not reflected in here. Yes? Yeah, they are given to us, and they are depicted here on the right-hand side. Yeah, that is why I showed you them before. Do you want me to explain it again? So, all right. So the question is like, why, I guess, please correct me if it's not the question, but the question is, why is 1.5 GE here missing, right? Why is this one not reflected in here? Okay. So let's think of it, how it could be implemented in hardware. Then you have your, maybe I draw it here. You have your AI, BI. First thing you do is like ending this, right? Then you have your AI and BI, and you do the XOR with that, first thing. Then the result of your XOR is AND C. So you have your AND and CI, and those two end up in a OR gate building C out, right? Can you see it? Maybe, okay. So this is like the logic or like the gate logic, how you could build up this function. And I hope now it's kind of obvious why we only have 3 gates here, because the critical path here is only this one, right? And this one just happens in parallel, yeah, right? So please ask if you have any questions. I'm here to answer those. So it's good if you discuss them also among each other, but I'm here for you to answer these questions. It's also okay if you just raise your hands during the exercises and ask questions. Please feel free so. Okay, so now we know the delay. What is the latency? So thinking of, okay, the delay is like 6 gate equivalences. But since we have a serial adder, we can only process 1 bit per clock cycle. Means to process all 16 bits of the full of the serial adder, we need 16 clock cycles to do so. Make sense? All right. Maybe let's have a look at the serial adder implementation again. And this is like a 16-bit value, right? So now you take the LSB, process the LSB. The result gets shifted in here. When does a shift happen? Every clock cycle. So you need like 16 clock cycles, so 16 shifts until the complete register A is empty and processed, and until you have your result then. Any other questions? All right, so then the next question is like, how would the metrics change if we use not a serial adder, but a 2-bit serial carry look ahead adder? The carry look ahead adder is depicted here, and now the question is, how would this change? So maybe we also start with this one. So remember, how do we get PI? So the question is first like, what gates do we need to calculate P0, G0, P1, and G1? This is PI first, and for that, we remember that we have a proper gate if A and B are unequal, so that's an XOR gate, and an XOR gate is just like 3 gate equivalents. And if we now have a look at how is S1 calculated, then it's like the XOR of A and B and the XOR of C again. And remember, how does C1 calculated? So C1 is this one, yeah? So the one that is fed in here, and it definitely depends on whether we have a generate 0 here or a propagate 0 and a C0 in. And so you can also depict this one here as A XOR B, XOR generate 0 or propagate 0 and 0. So what is now the longest path? This is now the big question. And
This is our formula. So this is like, why do we have a look at S1 here? Because S1 is like this one, and this is the bit that is having the longest path, right? So it needs to traverse all through here and through there to get here. So this is like the longest path. So this is the one we want to have a look at. And P0, now we know, if you remember, P0 already requires one XOR. This is the one here. Then the question is again, we're gonna have a look at this formula here. So we start with the most nested one, which is like this one, because here we also have this AND operation between P0 and C0. This is this one. Then we OR this together with G0. This is this one. And then we have one XOR with the result of this one. And here again, the exact same thing as before. The XOR of this one can happen in parallel to the calculation of this one. So this is why it is not reflected in here. And if we then do the calculations, we end up with 9 gate equivalents. All right. I give you like 3 minutes to answer this, discuss some questions. Mm-hmm. It's definitely a trade-off in the end. So it's like, it depends what improves, right? Because right now we're just looking at the longest path. So the frequency definitely increases. We're also gonna have a look at the latency. Maybe this also increases. And so then you're at least better performance-wise. But most of the time, a better performance also comes at a cost. And here the cost is like larger area. So you need to pay for that larger area on your chip. But if you were willing to spend them to gain the performance, that's okay. So this is like always if you are an engineer and you need to think about, okay, this is a problem at hand. You have multiple possibilities to solve that. And then the question is like, which performance do you need? How much money do you have to realize that? Okay, that's the question. Let me shortly have a look what is stated in the questions so that it's according to how we defined it here. No. Yeah, so the answer to that question is that it only is really the performance metrics, so latency and critical path. All right, so now we have calculated S1 here, which is the farthest away from C0 and the inputs here. But also the carry out is dependent on the inputs here and also on C0. So now the question is, maybe this path here might be longer than the path here, right? So that's the next question. Any ideas of what would be the first thing to do? First thing is like think about how do you calculate the carry out and come up with a formula for that. And depending on the formula, you can think of how many gates do you need to realize this formula and then come to your result. So another like 3 to 4 minutes for this one. All right, then let's continue. So what's the formula for C now? So we remember how to calculate the carry out for CLA logic. So we take the G1, if that is the generate, then we get a carry out, or we have a propagate at P1 and a carry in at P1. This is exactly the same thing as having a G1 or a P1 and G0 or a P1, P0 and C0. So now we have the assumption that this AND gate we need for the calculation of this here takes exactly as long as this AND gate that ANDs 3 inputs. So in the end, we have like one XOR, because remember, the calculation of P also takes an XOR. So for the calculation of P, we need one XOR. Then we have the end of this one, and we ORing it together with the other parts. And this gives us then in the end 6 gate equivalences. Questions? No. All right. So now the question is, how much latency do we get? Since we now use a 2-bit adder instead of a 1-bit full adder, we can now process 2 bits at a time. So during 1 clock cycle, we now process 2 bits. So we need 8 clock cycles to process 16 bits. All right, so just as a reference, the max delay here is 9 GE, and previously we had a delay of 6 GE. So this means that you can run the serial adder at a higher frequency than the CLA one. But the thing here is the CLA needs only 8 clock cycles in order to process the data. The serial adder based on 1 full adder needs 16 one. But the frequency here is cannot be double as fast as for the other one, right? Because here we have 6 GE, and for the other one it's 9 GE. So it cannot be double as fast. So this one would even be faster than in the end. Questions? All right, now the question is, we have 2 components again. Now we have a 5-input, 2-output lookup table, and we have 2-to-1 multiplexes. Now the question is, how can we build up a 16-bit adder using only these components? And remember that we have another objective, that the adder should have a maximum latency of 8 clock cycles. Now the question is, how do we realize this adder? So from the last question, we know if we have this 2-bit CLA, then and we plug this in a serial adder, then we come up with a 8 clock cycle delay. So why not taking this one in order to implement the 16-bit adder using just 5-input, 2-output lookup tables and 2-to-1 multiplexes. So this is like the idea that we are following. So once again, the formulas. So I hope up until here everything is what you've already seen. So this is how SI is calculated. This is how the propagate is calculated. So this is just like XORing. And this is how the generate is calculated. So this generate is just an AND operation, the propagate again, and this AND operation here. And now the question is, how do we come to the carry out? And there the trick is like, okay, carry out is nothing else than G plus P and CI. And now we can do a little trick and just add not P in front of the G, and it with P CI, or it with P and CI. So in the end, we just add this not minus. And now the question is, why have we done that? Any ideas? So what does this allow us now? Remember, we want to use a mux, right? So a mux has a select signal, which selects between inputs. And now the nice thing is following. We can use P and select between G or CI, because if P is 1, then we output CI. If P is 0, then we output G. So this is like how can you use a mux to come to that solution. And we use the serial adder again, right? But how does this look in the end? So now we have log A, B, a 5 to 2 lookup table. So this realizes our P and our G. So why does this work? If we have a look at the equations here, we know, okay, we have 4 inputs. A has 2 bits, so bit 0 and 1. B has 2 bits, 0 and 1. So this is like 4 input, perfectly fine for our 5 input lookup table. We have 2 outputs, P and G. So this is like the nice thing of lookup tables when you think about them, is you do not really care what logic functionality you want to realize. You only need to think about, okay, how many inputs do I have? How many outputs? Can I realize them using my lookup table? So if you have such a function here, you just count how many variables do you have. Does this align with the number of inputs? If yes, then you can place it in the lookup table. If you have another function like here, G, and you have another output available, then just use them, and you can also add them to the lookup table. So this is how we then generate P and G. And this is like now our trick. As I said before, we can use P as a select signal for a mux, selecting between G and the carry. And this gives us the carry out. And now the question is, how do we come to the solution? So to the bits that represent the addition. So exactly the same thing. We have a look at the formula here. See, okay, we have 3 inputs, and 2 of them have 4-bit, 2 of them have 2-bit, making all of them 4 bits, plus 1 bit for the carry, makes 5 input bits, which still suits our 5 input lookup table, so we can use that to generate both of our output bits. And now you take this, what is depicted in figure 3, and replace the full adder in the serial adder depicted before by this one, realizing the 2-bit CLA from the previous exercise. Questions? Anything I should explain again? No. All right. Then let's start with the next exercise. So this is about Coggy-Stone and Lardner-Fisher. So those 2 diagrams represent on the left-hand side Coggy-Stone and on the other side Lardner-Fisher. And what we want to do is we want to show the correctness and the functional equivalence by deriving the equation for the intermediate results. So the intermediate results are depicted here as 1, 2, 3, 4, 5, as well as here 1, 2, 3, and 4. And we want to show how are we going to do this. So I would suggest that we do that first for the Coggy-Stone adder together, and then you do that again for the Lardner-Fisher one. So what should we remember? So let's have a look again at the processing element. This is like our GI, PI, and GJ, PJ, and we process those together to get G out and P out. G out and P out can be forwarded to multiple other processing elements. That is why we have here like multiple arrows. And how do we calculate this one? This is just like, again, GI or PI and GK to get the new G out. And for the propagate, we just AND PI and PK. So this as a short recap. So now how do we come to the intermediate points? We just apply this formula, right? So starting with this point here, we just have to look up and see, okay, what inputs do we have? We have G1, P1 and G0, P0. And now we just plug them into this formula. And then always remember, starting from the left to the right. This is very important. We go from the left to the right. And here we then have G1 or P1 and G0. And for P1, we get then P1 and P0. Same thing for the other ones. We're looking up. What connections do we have? We have G2, P2 and the connection to G1, P1. So on the left side is G2, P2. On the right side is G1, P1. Plug that in, come to that formula. Same thing here. First going up, then to the right, and plugging in, coming to the formula 4.3. So now the interesting part begins. We have a look at this point here. And here, now the same thing applies, right? We first go up. There is an intermediate point. We use this one, apply the formula, and go to the right, which is this one, and apply the formula as well. So there we then get G of the intermediate 2 or P intermediate to G0. And for P we get P intermediate 2 and P0. And for P2 intermediate and G2 intermediate, we already have the formula here. Then we plug this in and come to the result G2 or P2 and G1 or P2, P1 and G0. This is for the generate, and for the propagate, we just have then P2, P1 and P0. And now for the last one, which is this one. This is our intermediate. We do exactly the same thing. We first go up, find another intermediate, use this one, then go to the right, find another intermediate, and use this one. Plug that in, and then come to this formula. And this is what we expect, right? So this is something what we always want in the end, this kind of structure. We want first to have a generate, then we want to have a propagate ended with a generate of the node right to it. Then we want to have two propagates with the propagate of the left node, with a propagate of the one right to it, with a generate again of one right to it. And then the next one, we have now three propagates and one generate for the last node here. And for the propagates, we want just to have all propagates together. It's like 3, 2, 1, and 0. So this is like the formal way of showing that this is what we expect and this is what we get, independently of how this looks like. As long as it realizes an adder structure, you will end up with formulas for C0, for this, and this, looking like depicted here, right? And now you can also have more a little bit like an intuitive way of looking at it. It's not like the formal proof, and if you would have been asked like, show that this is an adder, then this is not the answer. Don't give that as an answer. But it's like for you to get a gut feeling whether this adder you see depicted here in this PPA diagram is an adder or not. So the idea is like, if you see something like that, have a look at the left bottom part. There you have like C3, right? And then you want to look, what connections do you have? From this point, you want to have connections to all of those points. If that's not the case, then it's not an adder. From this point, you want to have a connection to this, this, and this. If that's not the case, then it's not an adder. From here, you want a connection to this one and this one. If not, it's not an adder. And here you also want a connection to this one. If not, it's not an adder. So this is like the first sanity check you can do. The second sanity check would be like, how do those connections work like? And there it's like, you always start at the left side, and then you start from the top to the bottom node. So first have a look at the top node, and then it's important that this is the one that connects to this one and to this one. Then we have a look at the one below, and this then needs to connect to the next one, so to this one. It wouldn't be okay if this node would connect directly to this one. That wouldn't be okay. And then you just move on. So this is like a first sanity check you can make, but it's not like that you need to do that. The formal way of showing is always like writing these things and then see in the end, okay, is this what I get or is it not? And if it's that, then you're sure it's an adder. If it's something else, it's not an adder. Question so far? No. All right. Then your task is to do that with the Lardner-Fisher. I give you 5 to 10 minutes for that. If you have any questions, please come and ask or raise your hand. All right. So then let's have a look at the Lardner-Fisher and see whether it's an adder or not. So hopefully it is. But same procedure as before. So for the intermediate nodes, we do exactly the same thing again. It's just plug and play. So for this one, we first take this one as the left side and this one as the right side. So this is I, this is K, and then plug it in, get the formulas. Then we do that for G3 intermediate again. So there we take G2 and P2 as I, and we take this intermediate node as K. Then we get this one, and if we plug in the intermediate node, we come to this result here, and this looks like that. And now the last one, same thing again. So we have a look at this node. We see going up first, we take the intermediate 2 as I, and what is K? We follow the path, finding intermediate 1, taking intermediate 1 as K, plug this in, and replacing all the intermediate nodes results then in this one. And if we now compare this with the adder we've seen before, then we see that this formula here, and the one above, so 1, are looking identical. They are exactly the same. All right, questions regarding the Lardner-Fisher adder? Yes, the 4. This one here, right? Yeah. So what you do is like you use this formula up here. So you just need to figure out what nodes do I need to plug in. First thing is we have a look at this diagram here, find the intermediate node, which is this one, right? Then we're gonna have a look at first going up, always first go up. Then you end up at this intermediate node here. So this is the one you're going to use as I, so this one. Then you go to the right, follow the path, and find this intermediate node. So you use this one as the K here, and then you write it in that kind of form, which is exactly this one. So far, okay? Okay. And then the next step is like, okay, here is now G intermediate 2. The question is now, what is G intermediate 2? We already defined it here. Here's G intermediate 2. And what does this correspond to? It does correspond to this part here. So you just plug this in and get this part. And this is something you do for all of those as well. And you end up with this part here. So this is the first thing. And maybe the interesting part, yeah. So here's like the interesting part, let's say. For this one is also the P and the G1 intermediate, and then you just kind of do a little bit of math and end up by this and this representing exactly the same thing. Other questions? All right. Then let's have a look at, we're going to look at this figure here, and we want to see, is this a valid adder or is it not? So maybe the first method to do that, which just like gives you a gut feeling whether this is correct or not, is like first trying, coming from here, I need a connection to all the 3 points above here. Is that true? I find a connection to this one, but I do not find a connection to this one, right? So this is why this presumably is not a valid adder, okay? But that's not how we can show it. So the way how to show it is formally writing the things we've done before. So just find your intermediates, do the calculation, the plug in of the nodes, and then see whether we find what we expect. And how do we do that? So first, we need to define some requirements, and then we're going to derive the equations. So this formula should look very familiar right now to you. And the expectation is like following, right? So we have the conjunction of Gi P1 with G0 P0 gives us the intermediate G1 P1, or the result of it, right? And the same for 2, and that's it. So if we go back to like the diagram like this one, so these are the 2's we need to find a formula for, and what we expect for those 2 is exactly what is depicted here, and this is like always the same. Now the question is, what do we have? So what do we have? Let's have a look at the right one first. Then we see, okay, we have conjunction between G1 P1 and G0 P0. If we have a look at it, so this is the node, right? We want to have a look at. We see conjunction of G1 P1 with G0 P0. Very easy. And then for the second one, we see we have this one. This is a conjunction of G2 P2 and G1 P1. And what we see now, does the right-hand side look exactly the same as the left-hand side? No, it doesn't. So this means this is what we would have expected. This is what we've got. So be aware of that, and we know it's not an adder. So the next question is, how can we make it a valid adder? Any ideas? So what is missing? So we're missing this part, right? So we need a conjunction to G0 and P0 for this node here. So if we have a look at the diagram, we're looking at this node here, and we're missing a connection to here. So we just need to add this. And one way to do that is just like adding another node below and connecting it to here. Now the big question is like, would it be also okay if this is above here? No, it wouldn't, because then we would first like connect. So if we would have it here, then something like this, right? In theory, would be a possibility, but then we have the problem that we have a conjunction of G2 P2 with G0 P0. And then it's not okay, because the order matters, right? We always need to have